Thank you. Nice introduction. Aloha. And I'm Lucio Lee. Today, I'm going to talk about future networks. Everybody knows the internet is one of the most successful technologies of our time. It has created millions of jobs, trillions of dollars of business. We use it to create content. We share content. We sell our products and services. But like any other technologies, it also has some limitations. Today, I'm going to share with you a new IP. It is a progressive and evolutionary change to the current IP. So it can help you to upgrade your network from best effort to high precision. We can use it to enable next wave, next curve of internet innovations. So you should care about the new IP if you make routers and switches, just like me, and if you operate a network. And if you also work in industrial verticals like industrial internet, cloud driving, and even in public service sectors. So I will start from Network 2030. That is an ITUT initiative. And then I will analyze the current IP's constraints and limitations. After that, I'm going to outline the new IP and highlight its major components and new ideas. I will conclude my talk with a short summary. So what will be the market drivers in the year 2030? That would be 10 years later from now. So it's very dangerous and risky to predict something in the future. And we already know very, very well about what has happened. People are always smart about the past and sometimes smart about now. So we see it, we can feel it about now. But what's going to happen like 10 years later? Especially if we predict something that is as dynamic and scalable as the internet. But we need brave people to do this job. So we need people to have courage to do it. Last year, taking a bold move by ITU, so they set up a focus group. It's called Network 2030. It's chartered to do 4 things. Number 1, identify future use cases and requirements. Number 2, study new capabilities. Number 3, explore new concepts, new principles, new architectures, and new mechanisms. And number 4, review current protocol stack and outline future developments. Since it was set up, we have already held 5 workshops and 5 plenary meetings in New York, Hong Kong, London, St. Petersburg, and Geneva. And next month, in January next year, we are going to have our next meeting, next workshop in Lisbon, Portugal. The meeting is open and free to everyone and to anyone. Feel free to come to Lisbon and join us. On my record, since it was set up, we have gained significant momentum. There are more than 80 organizations whose employees, scientists, engineers, directors, executives come to our meeting to give speeches, to make contributions. And so what they have done, thanks for this community, they have successfully identified 3 major market and business drivers. First, it's called very large volume and tiny instant communications. So in this category, we have holographic type communications, holographic teleport, and digital senses, tactile internet, and cloud driving or teledriving. The second, it is beyond best effort and high precision communications. This includes lossless networking, throughput guarantee, and in-time guarantee. The third one is many nets. It includes satellite networks, MEC and slicing, and some special purpose networks. So in the next few minutes, I will explain some of them. The first one is the holograms and the holographic type communications. Now we are in the age of AR, VR. But what is next after AR, VR? So holograms and the holographic type of communications will come into our life sooner or later. The University of Arizona did one experiment for a tile of 4 inches by 4 inches. It needs 32 gigabits per second. That is raw data. But for a person like me, this build, it would need 4.3 terabits per second. Of course, you can use compression technology to reduce it. No matter what, probably you still need 10 gigabits per second. Sometimes you don't even have enough time to compute the compression for real-time streaming. How about the latency? Latency is also important, especially for real-time streaming. According to some research, if you have 360 degrees of view, and you allow for 6 degrees of freedom, and the latency, we call that motion to photon time, is 20 milliseconds. In 20 milliseconds, you need to do framing, streaming, encoding, network transport, decoding, and display. But if you do a reasonable time budget, you only have 5 to 7 milliseconds for network transport, even though you can use compression to reduce the bandwidth or throughput, but you don't have time to compute them. So the high throughput and the latency are so important for holographic type communications. In addition to them, there's one more challenge. It's called coordinated synchronization of parallel streams. Like Taylor Swift is a singer. She's a pop star. Many young people like her. Suppose she sings in Las Vegas, but her musical band plays in New York, and her dancers dance in Paris. So in this case, we need to teleport the musical band and the dancers from New York and Paris simultaneously to Las Vegas. We need to synchronize all the music, songs, and the dances together. Every human being has 5 senses. We can hear something, we can see something, we can touch it, we can smell it, and we can taste it. So every human being has 5 senses. The first generation of media only has 1 sense, that is text. So you just see it. So now we have 2 senses. You can hear the sound, you can see something like motion, that kind of, so that is video. So 2 senses have been implemented in our media. But what about other 3 senses? IEEE has done something here. They set up an initiative called Digital Senses and Digital Reality. If we combine digital senses with holograms, the holographic object will look vivid and real. So in this case, the user would have truly immersive experiences. Of course, the challenges are also big. And another example, which I like it very much, and I live in the San Francisco Bay Area. The University of California, Berkeley, is nearby. On its campus, you can order pizza. The pizza will be delivered to you by by a robot vehicle. The robot vehicle is driven by a student remotely in Colombia. Colombia is a country in South America. So cloud driving here has many applications. For example, trucks in a building construction site, tractors and pickups in the agricultural farms, and shuttle buses between airport terminals and in industrial parks here. So how is that related to the network here? Especially like farmers may like it. For example, if the weather is bad, the farmers can work from home. They can drive like tractors, pickups, and remotely. In this use case, cloud driving, latency and packet loss are very crucial. For example, if you send an instruction, say, stop it. So the instruction on the network will take time. The shorter the latency, the safer. And also in this case, it's absolutely intolerable if you lose such an instruction. If you lose instruction stop, maybe you would have a collision here. Different driving speed needs different latency. For the robot vehicle in University of California, Berkeley, so they drive so slowly because the latency is longer because the driver is in Colombia. The tactile internet is a short latency combined with haptic technology. It can be used in some manufacturing facilities. Ultra low latency and packet loss are very important because you absolutely have no time to retransmit your packets. 10 years ago, there was only one internet, but now it's different. There are probably 7 to 8 internets here, but people just not aware of it. Some private companies are building satellite networks in the space. From news report, we already saw 4 such companies, and also some private companies also building their own networks here. So for the satellite network there, in the past you can use it as the access going up and coming down. Because more satellites are running in space, you can use it as a transport network. By itself, the complexity and the routing table, and it also qualifies itself as a network here. So there are some challenges here. I will talk more about it. And in addition to the emergence of satellite networks, there are 2 more challenges. According to Professor Mustafa Ammar of Georgia Tech, so the current internet is being segmented, and special purpose networks are using tunnels as an overlay on top of internet to connect them together. And Jeff Houston says that in a very influential speech, the public internet backbone or transit is disappearing because private companies are building their networks there. So user traffic is going to the private internet instead of the public network. Space internet, just one example of many nets. The current infrastructure is shifting from old one net to many nets here. In addition to satellite networks, we also see that some very big private networks, they are at scale as the public network. There are also some special purpose networks for IoT applications. The major challenge here is how to integrate and converge them with a terrestrial network here. And it's even a question if the private network owner are willing to converge their networks with the public networks here. So there's no policy, there's a legal gap here, there's no government regulations on this. And moreover, our technology is not ready for their convergence. So this is a short summary about applications and applications and requirements. So we see that all our current only solves one problem, that is connectivity, which make people and things online. But for future applications, we need some advanced capabilities like high precision communications, lossless networking, in-time guarantee, that kind of thing. Okay, so is our technology ready for it? How about counter IP? Can you solve those problems? This is a short overview. The internet is based on a very basic principle. It's called statistical multiplexing. Statistical multiplexing can maximize the link utilization. And the routers and the switches, so only provide three basic capabilities and services. First, best effort. That is the most popular, mostly used. Second, diff serve, in order to make a differentiation between voice, video, and normal traffic. Third, that's called traffic engineering. We can see that mostly in MPLS network cell. So in the internet, it's allowed to lose a packet. After you transmit the packet, after the packet is lost, congestion control is kicked in, and then you retransmit it. According to the Cerf-Kahn-Mathis equation, there is a relationship between throughput, latency, and packet loss. So it's good to have statistical multiplexing, but it's bad to have packet loss. But how can we do it? And if you look at the ACM sitcom, so congestion control never stops. Every year there are publications there. And if you are writing your PhD thesis, you can always pick up congestion control as your research topic. According to Google Scholar, there are more than 13,000 papers. If you read one paper one day, it will take you 36 years to read all of them. So basically in all the research, and either you do it on the end-to-end way, so you do it on the host operating system, or you do it in network here. So there are two categories here. When people do research, they always make one assumption for particular context. Then you design a mechanism, then you show that, oh, it's better than that. So obviously, no one size fits all. Moreover, very few of congestion control techniques have been implemented and available in commercial systems. And so this is an extrapolation from Cerf-Kahn-Mathis equation. Take a look on the second picture. Assume you want to have a throughput that is 12 gigabits per second. That's pretty much normal for AR, VR time streaming. And so in this case, suppose you lose a packet every 10,000 packets in the internet. That's very normal. So how can you do it? According to this equation, your latency has to be 0.1 millisecond. In reality, how can you do something like this? It's not feasible. So right now, everybody talks about the 5G. But if you look at the architecture, actually, there are two sides in 5G mobile architecture. On the left-hand side, it's radio. On the right-hand side, it's fixed IP MPLS network. So if we examine them in isolation, they are perfectly fine. There is nothing wrong. But if you put them together, holistically speaking, we can easily see there are 5 issues. Number one, in 5G, we are talking about ultra-reliable low-latency communications, URLLC. But TCP/IP cannot guarantee anything like that. So if you put them together, you cannot guarantee the throughput through TCP/IP here. The second issue is that radio reliability and the TCP timer and the flow control are not synchronized. They have different timers, which would cause your TCP/IP wastefully retransmit packets. Now, the third issue is that probably you can all see it. So we use tunnels over tunnels. But in mobile backhaul, we are talking about IoT, massive machine type of communications. For example, an electricity meter report your monthly electricity usage to a utility company for accounting and billing. The payload probably just 1 byte or 2 bytes But the header probably is more than 150 bytes, so it's making your efficiency very, very low. It's even less than 10%. So radio side try to increase the bandwidth, but on the fixed network side, because of this tunnel technology and it's offset the gain from the radio side, so it's not applicable to MMTC. We're also talking about the slicing. In IP, MP, LS, you cannot guarantee anything like latency, throughput, and so in this case, so this technology and tunnel technology dimly not applicable for 5G here. Moreover, we also have header and repetition, and header repeat each other. Okay, and taking applications and the current internet program together, what we would expect from the future networks, particular new IP. As we said, the current internet is essentially a best effort, but the future applications require high precision KPIs on throughput, latency, and packet loss. And it's mainly for the machine-to-machine communications for industrial manufacturing, control, automation. So that is number one. Number two, the current internet, the throughput is subject to the Cerf-Kahn-Mathis Equation, but we would expect that the throughput should be linearly proportional to bandwidth, and latency should be linearly proportional to physical distance. The longer the distance, your latency should be shorter. The higher the throughput, your throughput should be higher. So that would be the second expectation. The third is that because of emergence of many nets, new IP should accommodate many nets and provide for integration and convergence of all types of networks. In particular, it should provide for integration and convergence for satellite networks and terrestrial internet. So with those expectations, what should we do and how? And so now I'm going to start to outline new IP and focus on its new idea. So the design is very progressive and fully backward to the older technologies. So I noticed that for every major networking technologies, there are only 3 cycles here. So it always starts from the data plan and then moves to the control plan, like signaling, routing, and later goes to the management plan, orchestration, how to manage your network. For this new cycle, new IP, still the same thing. So I'm going to talk about new IP in the data plan. And later, after the data plan is implemented, of course, we need new routing technologies, new control plan technologies. So earlier in history, IP datagram actually is called a lettergram. It was designed to simulate the postal letters. A postal letter has an envelope and texts are put in the envelope. So the envelope later becomes IP header. The text becomes user payload. That was 30 years ago, but today the postal services are different. And in today's postal services, you can customize your delivery and requirement. For example, you can say that deliver this package in 3 days, or even next morning, or even on the same day. Of course, it depends on where the receiver is. And the user can track the delivery status in the postal system. And if the package is lost, the company will pay you a refund. It's called an insurance. Of course, for different delivery, you pay different prices. But IP was not designed this way. IP was designed like postal services 30 years ago. FedEx is a typical modern postal services. In a FedEx package, in addition to an envelope and a parcel, you also have an extra page, a paper. So on the paper, you can fill out how do you want to deliver your parcel, your package. You can say that, well, I want to deliver this package next morning, like before 9 a.m. If you cannot deliver, you should pay me a refund there. So can we design new IP, as a FedEx-like datagram? Not like a 30 years traditional, conventional IP datagram. Actually, we can. This is our first idea for new IP. So in addition to IP header and a payload, now we have a new component. It's called a contract. In a contract, you can require something, let's say, in-time guarantee. You want a packet get there in 35 milliseconds. You can require lossless networking, throughput guarantee. If your packet is not delivered on time or in time, the insurance company can step in to pay you the damage. We know that the insurance business is everywhere, but not in internet. But in the future, it's possible. So how contract is useful? Here I have a few examples. My favorite one is high precision communications, because I care about the industrial manufacturing. You can also build user network interface by using contract. You can build in-band signaling. In the internet, every signaling is out of band. You can even build up high precision telemetry. You can also have user-defined networking. So there are many, many applications. I know that quite some universities and PhD students, postdocs are exploring how to exploit contract to solve spatial problems, their spatial problems. So how about many nets, as said earlier? And many nets are emerging here, but different devices and in different domains may need different lengths of addresses. 32 bits, 128 bits are not applicable to everything. So sometimes people need like a very short length addresses. So in this case, we probably need to build a flexible addressing system in new IP so that you can unify all different networks in the same network, in the same routing table. And for the satellite, currently mostly satellite is used access. But at least the 4 companies are building satellite as networks here. So satellites is used to transport the network. But satellites are always moving. Satellite base station likes to transmit its signal in a fixed direction. How can we do this? So in this case, one address can be defined by using longitude and latitude. So that address would be 2-dimensional. And by using these 2 addresses, you can change your routing table so that satellite will look pretty much like a normal terrestrial networks. In the current IP, a packet has bits and bytes. We know that all the bits and bytes are equally significant. If you lose 1 bit or lose 1 byte, the sender needed to retransmit it. So we have a checksum. You do a checksum. If a checksum fails, the receiver will discard the packet. And then wait for the retransmission. So in this case, the latency will more than double the single transmission. The throughput is also reduced because of a smaller window. So bits and bytes are equally significant. We call that quantitative communication. Look at this picture. So on the bottom, the only difference is the color of the shirt. But for us human beings, they are really the same person. But for the internet, they are 2 different persons. Moreover, they think the second person is not right, so they discard it, wait for the retransmission. This is good for file downloading, for document transfer. When you do shopping, when you do banking, it's good. But it's overkill for some images, for holograms, are also in a disaster environment. Because in disaster environment, such as earthquake, you have no chance to resend your packet. You only have one chance. You have no sense. You don't have the second chance. And sometimes in a battery, when your battery runs out, you cannot transmit your packet. So quantitative communications is overkill for some applications. But how can we do about it? Here, in syntax, if we make a distinction between bytes or blocks or chunks in the user payload, we add something, we call that entropy. So if entropy is added to associate the bits and the bytes, we can implement something, we call that qualitative communications. Here I have 4 pictures here. On the receiver side, you can see that all of them are different from the sender side. But for human beings, they may still accept it as good packets. Because who cares, like me, like how tall I am, so which shooter, what's the color, nobody cares. You don't care about, like I have a long hair or short hair. If the packet provides enough information so that you can distinguish that, that's me, probably it's good enough, right? So it's called entropy-based communications. We also call that qualitative communication. So in this case, bits and bytes on the sending side are not the same on the receiver side, but their meanings, entropies, qualitative properties are the same. So here's an evolution map. As I said earlier, it's I want a new IP to be fully compatible with older internet. And here we have 3 stages here. The first stage is to add contract to the current IP, IPv4 or IPv6, so that we can achieve something we call that high precision communications. After we add it, you can implement it in some networks, let's say from 300 to 500 kilometers in diameter. That's pretty large enough for a metropolitan area network. We can use this technology to implement mobile backhaul to support MMTC and URLLC, massive machine type communication, ultra reliable, low latency communication. We can also use it in a manufacturing facility. Like if it's a campus, big campus, several buildings, we can use it. That probably is 10 kilometers. So in this case, we can achieve in-time guarantee, that kind of thing there. Second phase is about the header innovation. As I said earlier, because of emergence of many nets and satellites, we want to have flexible addressing system. And also we need some geography-based addresses, longitude, altitude, we can build them in. So after you build it, such a technology can be deployed in a satellite-based stations. That's still small scale. The third part is about holographic type of communications. Right now, we are working on the next generation web technology, vendors and designers and researchers. So for the next generation web, current web browser is 2-dimensional. Just imagine that you wear a gadget. Can you make your browser as a 3-dimensional, holographic based there? So you just wear it, you go there, touch here, see there, like 360 degrees. So in that case, you need a new IP, so you need a qualitative communication, entropy-based communication, and semantics-based communication. And so there are 3 stages here. So we are not looking for overhaul of every part of the internet, because this is for high precision. And you cannot have any latency as you want, because latency is still subject to the physical distance. Like every 1 millisecond, probably you have 200 kilometers. So if you want to deploy the 300 to 500 kilometers, you can pretty much achieve tactile internet. Because tactile internet typically requires sub-millisecond to 5 milliseconds. So we are living in the physical world. how can we develop the applications? People know that, and if you are an application developer, you really do not care what is inside the network. What you care is about the sockets. So you open socket, you build a connection, you fill out the socket options. But for new IP, it's still the same thing. If you want to have a MMTC application, you just open up a high precision sockets. So the sockets will hide all the implementation details, and then everything else will be normal and old in the older way. And so I know that. So currently, as I said earlier, more than 80 organizations, they are working on Network 2030. They have identified a bunch of new use cases and a bunch of new capabilities. So you can try those new use cases and new capabilities by using this new IP. So this is a short summary before I go. And the first point I want to make is that the internet is very successful and powerful, but it has some limitations. So future applications do require much more than the current internet can offer. The second is that although we have done something here, but for us, we still, there are more unknowns than knowns here. The industry needs innovations from all layers, especially from the network layer. So in the last 30 years, especially in the last 20 years, we see many innovations at the application layer, transport layer, layer 2, Ethernet layer, and also physical layer. But we don't see many innovations at the network layer. So I hope that new IP will be the beginning of the next wave of innovations. But its ultimate success will rely on wide and deep collaborations from many industrial sectors, academia, and standards development organizations. Thank you very much. I hope you enjoy it.
So thank you to our distinguished keynote speaker for a great talk. So here we have a couple of questions from the audience. So the first question, do you think we need new mobile equipment for users to support new applications such as holographic type of communications? So do you think the new equipment will still look like today's smartphones?
Actually, it depends on how you define this mobile, like a smartphone here. But for me here, let's say have a holographic concert. A cell phone definitely doesn't work. You need to build something we call that light field. So you want to have the same size concert or just like proportionally small size that. So when you deploy such a light field, it's very costly. So you need to go to special places like to watch a concert. So that's a light field. But we do need some gadgets. I already mentioned digital senses. For example, on Saturday night, it's rainy, it's very cold. You don't want to go out, go to a restaurant, but you want to order some food. So nice pictures are not good enough. You want to see how that is tested. You can build some gadget insert to your cell phone, and then you can smell it. So the gadget can produce some scents. You can smell it. Some startups are doing this, but it really depends on the content, how you define mobile phone. But I would say that the gadgets and some light fields, so that will be necessary for holographic concert. Yeah.
Thank you. Yeah. So the second question, come from the audience is in terms of wireless communications. So what's the main difference between holographic type of communication and a tactile internet?
Actually, so many people have defined the tactile internet as a special case of Wi-Fi wireless networks there. So everything it's a wireless. So that's just for me. That's just an access, or sometimes we call that last mile. Actually, it's not last mile. Like a few meters there. But for me here, I really care about industrial manufacturing. So here the tactile internet is a really short latency network combined with haptic technology. For example, let's have a ping pong game. So ping pong game, one side is a physical, like a player. The other side is a holographic player. But that holographic player is an image or hologram of a real player somewhere else. But it's not just a few meters, maybe in the same city. So in this case, you probably need a 5 millisecond latency. So for me, any network, it's under 5 millisecond latency. I would consider that as tactile internet, and also it provides some haptics there. So if there's no haptics and there's no tactile, it's really depending on how you define it.
Thank you, Dr. Lee, again, for the great talk.
Pleasure.
I'd like to invite Professor Ulema, Industry Forum and Executive Chair here to present a small token of appreciation.
Okay, thank you very much. Yeah.
Also, this is also for you.
Okay, thank you very much.